rules of the game.
All right, thank you, Ben. Next up, we have Victoria Stevens.
Did you get me a copy, Ben?
No, sir.
You email it to me, I think you did email it to me.
I'm bringing you a copy.
That's
Hi, my name is Victoria Stevens, and I'm from Group 2. And for Experiment 4, we did the vapor compression, refrigeration/heat pump. And in this experiment, we wanted to analyze the cycle, of the refrigeration cycle, and calculate the coefficient of performance, understand the vapor cycle, and then go through the thermodynamic properties of it. And so today we're going to go through a little overview of what we did, the data we got, and a comparison between that and the ideal cycle, and understanding the different parts of the cycle. In our governing equations for a coefficient of performance, we have our Q out of the condenser over the W in of the evaporator, and we also have our first law of thermodynamics. So this is a little overview of what we did. We went through this cycle, and we started at the top with the compressor, and we took the temperature and the pressure TS1 and SP1, and it went through the compressor. We got the main temperature at ST3. It went through the expansion valve and then back up through the evaporator to the compressor. And at the beginning, we took calculations at a flow rate of 5 liters per minute, and we found the power that comes out of the compressor, the temperature of the water to make sure that it's going from the inlet a lower temperature to a higher temperature. And from this, we've confined our coefficient of performance. And using this equation, we found a produced heat with our Q's equal to mCp times delta T. And we got a coefficient of performance of about 3.4. And ideally, we probably want about 1, but 3 is a really good number for what we got. For our case 1, we did a flow rate of 6 liters per minute. And here we have our main temperatures and our 2 pressures. So in the expansion valve and the compressor, we're worried about the pressure staying, and then in the condenser and evaporator, we're changing phases. And so this is our flow rate for 4.5 liters per minute, and then 3 liters per minute. And as the flow rate decreased, we kind of found that the temperatures increased. And with those data points, I kind of made an average of what it would be compared with our R134A for a coolant, and I plotted this, and we have with assumptions that the throttling is adiabatic, and then so we go through our evaporator up through our compressor and then into a condensing, and we assume that through the condenser the pressure doesn't drop. And that compared to our ideal, this is a pH diagram of a water diagram. We got pretty similar answers. So there were a few errors here and there that I made adjustments for, like how our temperature dropped through the evaporator, and ideally we want that to stay constant as it's changing phases. And through our expansion valve, which is changing the pressure from high pressure to low pressure. So as the liquid goes in, we're getting low pressure out, and the pressure is changing the diaphragm and like releasing less or more liquid. In conclusion, we found that through the phases changing, we have more. Through the phase change, we wanted constant temperature, and then as we're changing through the pressures, we wanted it to stay through the throttling adiabatic. In comparison from our refrigeration cycle to our ideal cycle, we found that there are a few changes, but not too many that we should be concerned about. And in our coefficient of performance, we found that it was about 3.4, and in before, for our group leader said that it was going to be about 3. Uncertainties that we could have found in our data would be the temperature of the heat sink compared to the atmosphere and like the temperature of the room. It could be something to do with the sensors and how that was calculated and programmed into the system, or errors in just our reading the sensors. So, any questions?
I think so. So why did you do the COPs for other two cases?
I'm sorry, what?
Why did you calculate the COP for the other two flow rates?
For the other two flow rates?
Uh-huh.
Well, we're given the pressure, the power for, at the beginning for the flow rate of 5, and so I use that.
No, but what about the other two flow rates? You could have got the new power too, right, from the compressor?
I think the power was pretty much the same.
So then you could recalculate your COP, right?
Correct, I could have.
You're correct, you did. And I have another question. If you go back to COP problem,
Yes.
your quotient of performance is Q out of the condenser or the work in evaporator.
So I use the work that, I mean the power here,
It's not
and then I
evaporator.
use the produced heat here.
But first of all, work into the evaporator makes no sense. It is work into a, not evaporator. That again makes no sense. It's not evaporator. It can't be. Where does the work go into a refrigeration cycle? Which device? Which one? Oh, the wrong part of pump. We call it a, the wrong part of pump at refrigeration cycle. That's the same idea. What do you call a pump that compresses gas? Compressor. A pump that pumps gases. It's a compressor, it's not an evaporator. Right? And you have another problem. Your numerator, right? I mean, your math might be correct, but your notation is wrong. It's work into the compressor. Right? The work is going into the compressor, not the evaporator.
Okay.
Right? And you have the numerator, which is Q out of the condenser. Now I'm really confused. If you draw your diagram for me, right? What is happening in the condenser?
It's so it's a vapor and it's that's a compressor. So condenser, it's changing phases.
Which is, if you go back to, is there another diagram of this cycle? Yeah, there you go. So where is the condenser here?
At the top,
So what is happening in the condenser?
it's changing phases. Right, it's going from a vapor to a liquid.
And which means it is, the refrigerant is, the refrigerant is losing heat or gaining heat in the condenser?
It'd be losing.
If it is losing heat, what is happening to the outside? So what is the diagram from 2 to 3 in terms of heat? Is the heat leaving the condenser or entering the condenser? Okay, first, okay, how will you write the COP, that COP term that you have written down? Is that for a refrigerator or a heat pump?
No, I'm sorry, what?
The COP term that you wrote down,
Yes.
is it for a refrigerator or a heat pump? That term there, quotient of
That term.
performance, is it for a heat pump or a refrigerator? Is there a difference between the COP of a refrigerator and the COP of a heat pump? Yes or no?
I didn't think so.
You don't think so?
No.
What's the difference between a heat pump and a refrigerator?
They do the opposite.
There must be a difference,
Okay.
right?
Yes, sir.
So draw me that in an undergraduate thermal class, how will you draw a heat pump and how will you draw a refrigerator? You know, we have a circle that represents the heat pump, we have a thermal reservoir, pH and TL. Remember the diagram?
Not really.
Anybody else? Yes, you can?
Yeah, it's like THTL in the cycle, and then it's supposed to go from hot to low temperature, but in a heat pump and refrigerator, it goes opposite, and the only difference is where you're standing, right?
There you
So
go.
whether you want heat or whether you don't want heat, whichever side of the heat pump you're standing on.
You must have seen this. So how will you do it? got? You know. So TH, high temperature, you got a heat pump. TL, you put work in, you're taking heat from the low temperature, you're putting heat to the high temperature. You can write heat pump here, or you can write refrigerator. It makes no difference. It's exactly the same thing, but the only thing that changes is, for a refrigerator, where am I sitting?
Right there.
Where?
Lower temperature.
Lower temperature. For a heat pump, I'm sitting up here. For you, a condenser represents the high temperature region or the low temperature region in the cycle. The condenser there.
The condenser there,
Does it represent, is it sitting at the high temperature or the low temperature in your cycle?
the high temperature.
High temperature. So if I'm sitting in the high temperature, I'm looking at this system like it is a heat pump. That is a coefficient of performance for a
Heat pump.
heat pump. But you need to find a coefficient of performance for a refrigerator. How are they related?
So they're the opposite. Well, like you inverse.
No.
No.
How are they related? You add one or subtract one. You guys remember that? COP of heat pump is COP refrigerator plus 1, I think, or subtract 1. I can derive it. I don't memorize it. There's a difference of 1 between the number. You want to go from the heat pump to the refrigerator, either you subtract 1 or add 1. I forget. So your numbers are off by 1 basically, because you did, I'm assuming everything is correct. What you have is COP for a heat pump, not for a refrigerator. Next.